The first idea we're going to look at, we have seen before. We've just seen a very simple idea of it where we could just quote pi times integral of y squared dx or so on. In extension 2, we're more interested in building the shape and seeing where it comes from and why we get that. And so the first technique is what we call discs and washers. So when we slice it, where we're going to slice the shape will be perpendicular to the axis of rotation. So let's have a look at something going around the x-axis. Here is a random curve, and we're going to find the volume from A to B around the x-axis. So my slice is going to be perpendicular, so it'll be a vertical slice. So I'm just going to, there it is. And what we do is we just investigate one of those slices. Now when I rotate it, I'll get, a disc. Like so. The height or thickness of the disc, if you like, is delta x, whatever the change in the x value is. The radius would end up being the y value at whatever point that slice is. And we would need that in terms of whatever the thickness is. So we need it in terms of x, so whatever the function is, that'll be our radius. So we can come up with an area for the cross-sectional face here, which is of course a circle. Pi times the radius squared. Okay. Which means the change in volume will always be that area times the change in the width. Now what we're going to do is sum up all of those. Every one of those particular discs or cylinders or whatever you want to call them. So it's the limit as that thickness approaches 0. Remember, it's the same idea as when we looked at area under a curve and so on. Ideally, we'd like the thickness to be as close to 0 as possible. And we're going to be summing from A to B. And there's our formula there, pi function x squared times delta x, which we know turns into the integral, because when we slice up all of those particular functions, we get the integral from a to b of function x squared dx. Now, I guess here's the difference between 2-unit, 3-unit and extension 2. In 2-unit, 3-unit, you simply jump straight to this step where you say volume is pi times the integral of y squared dx. In extension 2, we're probably more interested in how you create that formula. About the y-axis, will be a very similar idea, of course. There's my random curve, y equals function x. But we're going to go around the y-axis, so from C to D. But this time my slice will be horizontal, so I'm going perpendicular to the axis. That will once again become a disc. The thickness in this case now is the change in the y. So my radius, which would be the x value, but I need that in terms of y. So I'd have to rearrange my function here and make x the subject. So I'd come up with some new function, but in terms of y. The area of the cross-sectional face leads us to our, what we call the element, or the volume element. So the change in v, or delta v, pi times gy squared delta y. So we want to sum up all of those going from C to D, and we know that sum becomes the integral. Let's have a look at an example. So we've got our function y equals 4 minus x squared, which is of course our upside down parabola. There we go. And we're going to rotate around the x-axis. So take a slice perpendicular. The radius is the y value, which in this case we want in terms of x, so 4 minus x squared. Area of the cross-sectional face, which creates our elements of volume. But you'll notice I've expanded out the 4 minus x squared there. Which means our volume, a lot of times these integrals turn out to be very simple integrals. Which is why the setting up's the important part. I mean, if you look at the actual integral I'm doing here, it's hardly a 4-unit level of an integration. The key is getting there. That's what we're interested in. You know how to build it and come up with our integral. And in this one there is 512 pi on 15. Okay, going to do the same one, but the advantage of using this idea is I don't have to rotate around the x-axis or the y-axis. I can rotate around any line. So let's do the same thing, but now I'm going to rotate around y equals 3. So same parabola, but now I'm going to rotate around y equals 3. So those points of intersection will become important because I'll need to know the values that I'm going between. Taking our slice, but now the slice stops at y equals 3. So if I draw my shape in there, there's delta x. The radius now is not the y value. Top boundary minus bottom boundary. Now the bottom boundary is a fixed 3. So our radius will be y minus 3. So 4 minus x squared minus 3. We get 1 minus x squared for the radius. And then it just becomes the same idea. So area function, the element of volume, set up the limits, and then convert that to an integral. But you'll notice I've taken advantage of the symmetry here, and I've said it's twice from 0 to 1. Alright, so we get 16 pi on 15. Alright, let's do one where we trap an area between two shapes. So we've got two parabolas. One's the normal way, one's the sideways parabola. Y equals x squared, x equals y squared. We're going to rotate around, which one is it? We're going around the y-axis. So my slice will be perpendicular, which will be horizontal. But when I rotate this one now, I get a washer rather than a disc. So I need to find the outside radius, which would be the radius to the red curve. I need to make it so y, it's in terms of y, so we get y to the power of a half. And the blue curve, it's y squared for the radius. So my area here will be pi times the outside radius squared minus the inside radius squared, creating our element of volume, and tidying it up we get y minus y to the 4, well pi times that. And so we're going, it's the y value, so we're going from 0 up to 1, and we integrate, and eventually bingo, come up with our answer of 3 pi on 10. Here's one from an HSC. Quite a while ago now. 1996. Interesting way of writing it. If you actually look at it, it's actually just a parabola on its side. But they've written it as x plus y squared equals 0. So this particular red shape, we're going to rotate around x equals 4. And so we'll end up with, well, I know what I'd call it, I don't know if you know what I mean, a grommet. You ever seen them? It's like, you know, black rubbery things that sometimes you put in between pieces of metal to stop them rubbing against each other. Oh, okay. But those ones tend to be like plasticky, so they're spongy, so it's got a bit of give in it. Whatever. Alright, what do we got? So they've defined everything for us. When the region is rotated, the line segment, so they've called the slice a line segment, it will create an annulus. That's a technical name for a washer. So they want us to first of all show the area of the cross-sectional face. Alright, so we'll have an inside radius, which I'm calling little r, and an outside radius, which I'm calling big R. Let's go back to the picture. Got to be careful here, because the centre is over here at 4. So the inside radius would be to the line 1. So it doesn't matter, as you go down that shape, we can see that's a constant amount each time. This is going to be 4 minus 1, which is 3. Okay, so that's the inside radius. The outside radius will always be 4 plus the x value?
Negative.
No, minus the x value. Right, so don't let the fact that it's on the other side deceive you. It's always going to be minus the x value. It's just that it's gone over into the negatives. But because you're substituting a negative number for x, it will become bigger, because you'll go 4 minus minus, and you'll get a bigger one. So it is still 4 minus x, so we'll end up with 4 plus y squared. So we have 4 plus y squared and 3. Okay, outside radius squared minus inside radius, and sure enough we get the answer they're looking for. now it says, hence find the volume of the solid. There's our volume element. So we're going to sum up all of those. We're going from -1 to +1. Again, I can take advantage of symmetry there, because if you look at it, it does have that reflectional symmetry, but in this case, it's in the x-axis. And there's our answer. Alrighty. So I've picked some out of Cambridge, some out of Patel.
More out of Patel.
Enjoy.